Right, this is number 50. We have a quadratic graph for f. So my derivative is going to be linear. My second derivative is going to be constant. So we'll look at this from a couple of perspectives. The first is I could plot the vertex at 1, -1, and I can see another point on the graph at 2, 0. So I know that this graph is going to be like I could actually get the equation of the graph. We could say y equals x minus 1 squared minus 1. So 1 to the right, down 1. And I could actually work that all the way out, take the derivative, get the actual line. So maybe I do that for this problem. Normally you won't be able to do that, but we could for this problem, so we could get it more specific. And I think that's what I did maybe on the answer key. But let's look at it from the other perspective. The other perspective is using what you know about increasing and decreasing functions. This is a summary chart. You can kind of copy this down and use it for all the problems. Something we would have gone over in class that relates the derivative, the second derivative, and the original function. So right now I have the original function and I can see where my original function is increasing or decreasing, right? I can see that on the graph. So that tells me where my derivative is going to be positive or negative. So I can see that my original function is decreasing from -infinity to 1. So if I drew a line right here, since I'm decreasing from -infinity to 1, I know that my derivative graph will be negative. Since I'm increasing from 1 to infinity, I know my derivative graph will be positive. So if I were to graph the derivative without knowing the slope of the line, I know that I have to have some kind of 0 at the point 1 comma, well not, well yeah, it'd have to be a 0 at 1 comma 0 for my derivative graph. Now what I don't know about the derivative graph, just using this technique, is I don't know how steep it is. So it could be something like this, where it's a little bit less steep, or it can be really steep of a curve. Now since I know the quadratic function, it's just going to be a normal x squared plus bx plus c, I know my derivative is going to have a slope of 2. So I could start at 1, 0, and then try to go to 2, 2, and make the line go through those 2 points. That's my derivative graph, since I know it's going to have a slope of 2. But the connection here I want you to see is that the relative extreme of the original function, the relative extrema, this relative min, is going to be the same x value that you're going to have a 0. And that shows right here, where the derivative is equal to 0, I have a critical number, or possible extrema. Right? Critical number of the function is defined where the derivative is equal to 0 or undefined. And that's either going to be a relative min or relative max, or possibly a relative min or relative max. And again, if I'm doing something that's not a quadratic graph, or I can't tell exactly what the slope of the derivative would be there, I do know regardless that it's still going to be a 0 at that point. And I keep using the f of x, I mean f prime. All right, then from my second derivative, I can tell on this entire curve that this entire curve is concave up. Okay, everywhere it's concave up from -infinity to positive infinity. That means that on my derivative graph, the blue line, the derivative graph is always increasing. And that tells me that the second derivative is always positive. Okay, again, if I go back and look at my chart, I can say that the original graph is always concave up, which means the derivative is always increasing. We can see that with our blue line, which means the second derivative is always positive. Well, if it's always positive, it's either going to look something like a quadratic, or it could look, like a constant line. We know it's going to be a constant. Because the slope of this blue line is 2, we know that the second derivative is always equal to 2. Wrong line tool. So the second derivative is going to be y equals 2. Which is always positive. Sometimes I don't know what that value is, but I'm going to use these tools to get an estimate for where the graph is under other circumstances. For this specific problem, you could be very specific and get accurate graphs of each of them. But for other problems, we'll be a little bit more general. But we're going to use this chart quite a bit as we go through the other problems.